All right, today we're going to dive into one of the most foundational and, frankly, one of the most unsettling ideas in all of computer science. It's a story about this absolutely brilliant piece of code, a super clever trap, and a deception so deep, it really makes you question the very nature of trust in our entire digital world. And it all kicks off with this one question. It was posed way back in 1983 during a Turing Award lecture, which, by the way, is like the Nobel Prize for computing, so it's a huge deal. Now, on the surface, it seems pretty simple, right? But believe me, the answer, it just spirals into this totally mind-bending paradox. And the guy who asked it, yeah, he wasn't just any programmer.
We're talking about Ken Thompson, one of the co-creators of the Unix operating system. You know, the thing that's pretty much the bedrock of everything from Mac OS to Android. So yeah, a legend. And when a mind like that decides to tell you about what he calls the cutest program he ever wrote, you just lean in and listen. Because you know you're about to see the very architecture of our digital lives get turned completely inside out.
So, Thompson laid out his whole argument in 3 stages. And the first one? Well, it doesn't start with some grand conspiracy or anything like that. Nope. It begins with a classic programmer's puzzle, kind of like an intellectual game.
So here's the challenge for you. Can you write a program that, when you run it, prints out a perfect character-for-character copy of its own source code? It sounds like a total paradox, right? It's like trying to lift yourself up by your own bootstraps. But here's the thing, it's totally possible.
This little piece of magic is called a self-reproducing program. It's basically a piece of code that has 2 things, a complete description of itself and the instructions on how to print that description. And the logic behind it, it's actually surprisingly elegant. And seriously, you don't need to be a coder to get this. Just imagine the program is split into 2 halves. Let's call them Part A and Part B. Part A is the code, the instructions. It's like a recipe that says, first print everything in Part B, then print me. And Part B? Well, Part B is just a big chunk of data, a block of text that just so happens to be an exact copy of the text in Part A. So the program runs, it prints the data from Part B, which is the code, and then it prints itself. And boom, a perfect copy.
Okay, so here is the absolutely crucial point. This whole self-copying thing, it's completely indiscriminate. It doesn't care what it's copying. If you add a comment or any other little piece of code to the program, it just gets copied right along for the ride. This idea of excess baggage is the very first clue in Thompson's big demonstration. So hang on to that thought.
All right, on to the next piece of the puzzle. And this is where things get a little weird, a little self-referential. We're going to talk about the very tools that programmers use to build software.
You've probably heard of a chicken and egg problem, right? Well, this is a classic one. See, a compiler is basically a translator. It takes human-readable source code and it turns it into machine-readable binary code that the computer can actually run. But here's the twist. The C compiler is itself written in C. So how do you compile the very first compiler? It's a really deep concept, but what it means is you get this situation where a compiler can literally teach itself new tricks and then pass that knowledge on forever.
Thompson gave this just brilliant example to explain it. Let's say you want to teach the C compiler a new shortcut. V will mean vertical tab. Now, if you just add that rule to the compiler's source code and try to compile it, the old compiler just chokes. It has no clue what V is. So you got to train it. What you do is you temporarily write the rule using the number for vertical tab, which happens to be 11. The old compiler understands numbers, so that works. It spits out a new compiler. And this new compiler, it now knows that V means 11. So now you can go back to the source code, use your nice clean V shortcut, and the new compiler understands it perfectly. It then creates the next generation of the compiler, which also understands V. See? The knowledge is now self-perpetuating.
Okay, so we have piece number 1, the self-reproducing program, and we have piece number 2, the self-perpetuating compiler. Now let's watch how Ken Thompson combines these 2 ideas to create the ultimate betrayal of trust.
So on the left, you've got your normal, everyday, trustworthy compiler. You give it code, it compiles the code. Simple. But on the right, that's Thompson's monster. It has 2 secret, hidden instructions. First, whenever it sees the source code for the system's login program, it quietly injects a secret backdoor, a password that'll let an attacker right in. And then, and this is the truly evil genius part, whenever it sees the source code for the compiler itself, it injects the code to recreate this entire Trojan horse.
And here's how the attack actually plays out. It's a 3-step process. First, you create the Trojan horse. That's the part that adds the backdoor to the login program and the part that teaches the compiler to reproduce itself. You compile that with a normal compiler, and you get your first infected version. You install it. And now for the magic trick. You go back to the compiler's source code and you delete every single trace of the malicious code. The source code now looks perfectly clean, totally innocent. But when you use your infected compiler to compile that clean source code, the compiler recognizes that it's compiling itself, and it secretly injects the entire Trojan horse right back into the new version it's making.
The attack is now a ghost in the machine. It's not in the source code anymore. It only exists in the compile program, the binary executable. I mean, you could have a whole team of experts pour over the source code for weeks, and they would find absolutely nothing. They'd declare it safe. But all the while, the compiler itself is just perpetuating the lie, passing it on from one generation to the next.
So you see, this elegant and honestly terrifying demonstration isn't just about one little compromised program. No. This strikes at the very foundation of how we build and trust all software.
And that leads us to Thompson's really stark conclusion, which he delivered with a little bit of dark humor. He basically said, you can't trust code you didn't create yourself. Looking at the source code won't protect you. The only way to be absolutely 100% certain is to have built every single tool from the ground up yourself, which is, completely impossible.
And don't think for a second this is just some hypothetical problem with C compilers. The exact same logic applies to any program that handles other programs. We're talking assemblers, loaders that put programs into memory. You could even hide it in the microcode, the super low-level instructions that are literally baked right onto the processor chip.
The logic here is just inescapable. The deeper you hide this kind of bug, the more fundamental the tool you compromise, the more impossible it becomes to ever find. A Trojan horse hidden in the hardware itself? I mean, for all practical purposes, that would be a perfect, completely undetectable crime.
But Thompson wasn't done. He saved his final remarks for a really sharp moral and ethical warning, and honestly, it's probably more relevant today than it was back then.
He really took aim at how the media and movies were starting to romanticize hackers. You know the trope, these brilliant whiz kids, these anti-establishment heroes. Thompson just cuts right through that myth. He's like, no. What they're doing isn't amazing. It's vandalism, it's trespass, it's theft.
He argued that we needed a major cultural shift. He made this great point. It doesn't matter if your neighbor forgets to lock their door. You still don't have the right to just walk into their house. And it should be the same way with computers. Unauthorized access isn't a game. It's a fundamental violation. It's a crime that needs to be treated with the same social seriousness as a physical break-in.
And so that's where we're left. Thompson's cute little program pulls back the curtain and reveals that our entire digital world is built on layers and layers of trust. Trust in compilers, trust in hardware, trust in the thousands of people who wrote the code we use every day. But what he showed us so brilliantly is that this trust can be betrayed in a way that is fundamentally undetectable. And it leaves us with this one final really unsettling question that we should probably think about every single time we pick up any piece of technology.